everyone. How's it going? My name is Liz, and I'm from the Dfinity Foundation, and welcome to Community Conversations. It's an opportunity for you, the community, to hear from contributors in the internet computer ecosystem, as well as ask them questions live. So today, we have our very own engineering manager, Manu Drijvers, here to give a talk on how canisters can get access to secure randomness. So Manu, feel free to take it away.
Yeah, thanks so much for the intro, Liz. I'm excited to present this to you all today. So let me share my deck and then we can get started. So the topic today is randomness for canister smart contracts. So I'm going to try and maybe talk for like 20, 25 minutes about what we try to achieve here. I'm going to try and explain why it's actually kind of a challenging problem, and then take you through sort of the design, like how we landed on the design that we now have on the internet computer, how you can use that, and then we can go into more Q&A. So let's dive right in. So I guess as you know, many applications, many software applications want to use randomness. This is very useful for many different things, and dApps are no different. So we want that the internet computer supports dApps that can use randomness. This allows people to build all sorts of cool applications like we see on the right. This is a screenshot from a dApp that one of the community members made. It's called cycles.bat. What you can do there is you can ask the dApp to roll the dice for you, and you can bet on whether the sum of the two dice is going to be less than 7 or more than 7, and you could bet some cycles on that. Then if you're right, you win, and if you're unlucky, then you lose. That's just one example of what you can do with randomness. There are many more. And yes, as I said, we want to offer this feature to developers that choose to build dApps on the internet computer. So we want to make this easy for them, right? I think that's very important. We want the access to randomness be like efficient, fast, and not expensive or so. We want it to be secure, right? So if I were to make this app, I wouldn't want to lose cycles all the time because people can game the system somehow, right? I would want it to be fair, such that the odds are like they should be. And building on that security, we want to avoid adding more security assumptions than we already have in the internet computer. So I guess we already need that, like, the majority of a subnet blockchain is honest. We don't want to add new security assumptions to that. And this is actually a pretty challenging problem. So I'll first show some examples to kind of get a sense of why this is not so easy. So in the blockchain space, the whole approach is that many nodes or many replicas together agree on a blockchain, which means that they agree on which messages to execute and what the resulting state is. So they should all compute the same thing and come to the same conclusion so that they agree. Now you can already see that this is difficult when it comes to randomness. They cannot just take some randomness locally and then use that, because then everybody would get their own answer and there would be chaos. So we need some sort of common randomness or common pseudo randomness somehow. And some approaches are kind of discussed in the space. One approach is sort of relying on some external oracle. So you could imagine that in the bottom you see some blockchain. Maybe in block 1002, I place a bet on cycles.bet where I bet that we're going to roll less than 7. And then a couple blocks later, maybe the oracle comes and provides the randomness to the betting dApp, which will then decide whether I win or lose. Of course, this is possible, but now we need to trust this external oracle. So this is not what we want to do if we want to keep the security assumptions limited to the internet computer. A different approach would build on the observation that typically in blockchains, you already have some random looking values around anyway. So maybe you can leverage that. So for example, in a proof of work blockchain, you have these proof of work hashes that are hard to predict beforehand. So they might seem like a good source of pseudo-randomness. And the good thing is that because we already agree on the blockchain, this could be like agreed upon pseudo-randomness. In proof of stake blockchains, you could imagine something similar with cryptographic signatures. But I think this is not a very optimal approach either, because again, let's say I place my bets in a block, and now maybe a couple blocks later, the dApp is programmed, the smart contract is programmed such that it looks at the latest proof of work hash and now uses that as like a random seed. And this will now determine whether I win or lose. So if everybody would be honest, this would work. But these blockchains are meant to work in the scenario where not everybody is honest, right? Some block makers or miners should be allowed to be malicious and the system should still work. But in this case, that actually is not the case. It doesn't actually work. So suppose I not only place my bet, but I also control some miners or some block makers. And I actually created this block 1005. Now with that, I have all the information to determine whether my bet would be a success or not, whether I win or lose. And now if I bet a lot, I might care a lot about the outcome. And maybe I see with this block that I actually found, maybe I realize that I'm going to lose my bet. So now the obvious thing to do is just hide my block. I'm just going to not tell anybody about it and keep it to myself and wait for somebody else to propose a different block at that height. And hopefully I am lucky, and now in that other block things are going better for me, and maybe now I win. So I'm lucky, I win my bet. So this shows that this approach is kind of flawed in the sense that if the block makers, if the miners are not all honest, there's room for bias. Finally, there's even more complex approaches where you essentially run like a distributed randomness generation protocol on chain in like a smart contract. Clearly, this is not easy to do for a developer, and it also requires no trust assumptions. So there are some projects that go into this direction, and I think that's possible, but that's not what we wanted to do on the internet computer. We wanted to offer something more easy to the developers. Okay, so I guess hopefully by now you're convinced that this is a difficult problem. Let's now dive into the internet computer protocol and see how things work there and how we want to fix this problem. So as you may know, the internet computer consists of many subnets, and each subnet is a blockchain system. Here we're going to look at one subnet, but so it's good to remember that there are many subnets in the system. And in one such subnet, we have one blockchain that I try to show you here. So you see a blockchain up to height 29, and you see these diamonds on them with an N in it. Those are notarizations. So you see that each block in this chain is notarized. In our system, that means that this block has gained sufficient approval from different replicas in the subnet that they all put their stamp of approval on, saying, I think this is a valid block. So we know that notarized blocks are sort of good. We can build valid blockchains out of notarized blocks. But we might not reach agreement yet. So for that, we have another such diamond with the F in it that is the finalization signature. Whenever we reach such a signature, the protocol guarantees that by then we must have agreed on the blockchain. So there might be forks in the chain from notarized blocks, but once we have such a finalization signature, we know for sure that we agree on the blockchain. Another special thing about the internet computer consensus is that we only order messages. The messages are not executed yet. Instead, whenever blocks are finalized, the corresponding state is computed asynchronously. So to compute state 28, we could take state 27, the previous state, and execute all the messages from the finalized block in block 28. And so this is exactly the step that we need to be deterministic. So everybody should, from the same blockchain, be able to compute the same states. We have one interesting thing that you might have heard of. This is the random beacon. So at every height, we have a special artifact that is called the random beacon. And this is an unpredictable value that appears every round that the replicas create together. And we use this in our own consensus protocol to, for example, rank the block makers to select who's most important, who has priority to propose the block the next round, and things like that. Since this talk is about randomness, this sounds like a promising lead to look into. So let's look a little bit deeper into the random beacon. And to do that, we first look at threshold signatures. Threshold signatures are very special cryptographic signatures with very special key material. So on the left, you see the key generation process, and this is a distributed process. This is a protocol that we call distributed key generation, where nodes can come together and send messages to each other. And eventually, the process is such that there is one public key coming out, which is the colorful key that you see there. And each replica obtains one secret key share, so which is a part of the corresponding secret key, but not the whole secret key. Now, with this special key material, we can create signatures. So each node that has such a piece of the secret key, if it wants to sign a certain message, then it can take its own part of the secret key and create what's called a partial signature. So this is not a real signature yet under the overall public key, it's just a part of it. And now if sufficiently many nodes do the same thing, so if sufficiently many nodes say, I also want to sign this message with my piece of the secret key, and we have sufficiently many partial signatures, then we can take those and squeeze them together to form a full signature on the message. And such a full signature can be verified against the overall public key. So to verify that, you don't need to know exactly which nodes helped out in creating the signature, who created the partial signature. This is no longer relevant. You can just verify the whole thing with respect to that one public key. So this is a very nice property. And this is what we use to construct the random beacon. So the random beacon is constructed from threshold signatures, and to be precise, from threshold BLS signatures. So every random beacon the random beacon at height x is essentially such a threshold BLS signature on the number x. And BLS signatures have really interesting properties that make this a secure construction. The important property is that a BLS signature is unique. So what that means is that there exists only one valid signature given a public key and a message. So there can only be one right answer. So if we use this as randomness, you can imagine that like trying to bias it is really important, right? Maybe I'm thinking maybe I should contribute my signature share, or I shouldn't, or I maybe alter my partial signature. None of this can ever result in any bias, because there is just exactly one valid signature on the message. So there's no possibility of bias. This is very nice. Now you might wonder, but then is it still unpredictable? And the cool thing is that it is, because the threshold signature can only be constructed from sufficiently many partial signatures. So sufficiently many nodes must contribute such a partial signature. Only then can we squeeze them together to find the full signature, the full random beacon. And under our assumption that the adversary controls less than a third of the replicas in our subnet, and since we need more than a third partial signatures to create to create such a threshold BLS signature, this means that the adversary cannot on its own like compute the random beacon ahead of time. So they can only be known when the time is right, when honest replicas help out. And finally, it's also unstoppable in the sense that it only needs f+1, so more than a third of the replicas to participate. So even if some replicas are unavailable, or down, or are malicious and try to stop the system, this doesn't work because we only need f+1 replicas. So we should always be able to make progress. Okay, so this is some really nice randomness. These are a lot of nice properties that we already have here. So now one idea that we could explore is, can we maybe use the random beacon as the pseudo-randomness for the deterministic execution? So in this picture, could we maybe, when we compute state 24, not only take the block 24 in, but also the random beacon at height 24 and use that as the randomness? Now, the answer to that question is no, this would be insecure. And I'm going to argue now why this actually does not work. So suppose that the blockchain grows a little bit and I place my bet again. I'm again betting on that the dice are going to be less than 7. But as it so happens, there might be a small fork in the blockchain. This can happen under, if the network doesn't work so well, or if some replicas are malicious. But this is completely fine because these are just two candidates. And at some point, the finalization process will choose one of the chains. But now you actually can see that there's a problem already. My bet is placed in the block, and the random beacon is already available. This means that all the information exists to know whether my bet is going to be a winning one or a losing one, because this is computed from the blockchain and the random beacon, and I have those already. So I know exactly whether I'm going to win or lose. But the issue is that my bet is not final yet. It's not adopted in the finalized blockchain just yet. And so what I can do now, if I am maybe also a block maker, I can now look at whether I win or lose. And if I win, I build on the fork which includes my bet. And if it's a losing bet, I build on the fork that does not include my bet. So here we have a very similar problem to what we saw before, which is that block makers can now actually cheat and make it so that I never lose, never have a losing bet. So the issue is that this random beacon is known before the messages are finalized, before the blockchain is final. And now we get to how we want to solve this problem. So we introduce a separate artifact, which is just like the random beacon, what we call the random tape. It's also created from a threshold BLS signature. So we also sign something like the round number, but it has one important difference. So now in the picture of the state of a subnet, you see that we at the bottom still have the random beacon, but now towards the top, we also have the random tape artifacts. The key difference is that as the notarized blockchains grow, the random beacon grows with those notarized blockchain. And we need to do that because the random beacon ranks the block maker. However, the random tape does not grow yet. The random tape, we only compute the next random tape when the height is finalized. You see that we have some forks here, so we haven't finalized anything yet. And now maybe that top fork becomes the final blockchain, and only then are the next random tape artifacts constructed. And then the corresponding states are computed from the block and this random tape artifact. And now I claim that this is secure. And that is because we only ever create the randomness for messages that are in finalized blocks. So suppose I place a bet. At the point when I place my bet, I don't know yet if I'm going to win. And then first is adopted in the finalized blockchain. So I cannot get out of executing my bet anymore. It's set in stone. And only then is the corresponding randomness computed that my bet will be executed against. So even if the block makers are colluding or influencing things, this does not help in trying to win the game. Okay, so this is a secure solution. It just has one downside, and that is that we add latency to the system. It's not a very efficient approach because every block now first needs to be finalized, and then we do another round of interaction with the replicas to construct this random tape artifact, and then we can execute the messages. And of course, we want the latency to be very low. And we don't want to delay the execution of all messages just because some messages want to use randomness. So we make a slight tweak to this approach, which is that we actually create the random tape one round earlier. So as soon as the previous block is finalized, we create the next random tape artifact. That means that blocks can be executed as soon as they're finalized, because typically creating random tape should be faster than agreeing on a block. But now you should be worried because the random tape might have been known before the block is final, opening us up to attacks again. So what we do is we make it so that requests for randomness are asynchronous. So you don't get an immediate answer. So whenever somehow a canister smart contract needs randomness, it asks for randomness, and then it's paused there. And in the next round, it will only get an answer to the randomness request using the random tape from the next round. So this makes sure that we still have this property that the randomness that you get to process a message is always generated after the message is finalized. So this is exactly the situation that the situation that's running now. Let's look a little bit closer into how exactly this works in the deterministic execution part of the system. So it starts as an execution round. We have some randomness, right? Some random tape. And the first thing that it does is derive multiple pseudorandom number generators for this. This is because execution uses multiple threads and each thread wants to have its own randomness. So we create many independent pseudorandom number generators from this one random tape that we use as seed, essentially. Each thread processes a subset of the canisters. And maybe some of these canisters have made a request for randomness in the previous round, which we just said is asynchronous. So we have some piece of the state that says, here are the outstanding randomness requests that are still waiting for an answer. And so now using the pseudorandom number generator, we can give those answers back to the canister. And of course, we process the messages from the finalized block in this canister as well. And the canister, during this processing, might request more randomness via some randomness API that we expose, which are then written back into the outstanding randomness requests. And then in the next execution round, those requests will get an answer from the next random tape value. Okay, so this is an API that is being offered in the Internet Computer. I think this is a very cool feature that the system has. I linked some pages here to the SDK that shows how you can actually start building on this, how you can make use of this. And that brings me to the summary. So we've seen that randomness is very useful for many things, but doing this in the blockchain setting is really difficult because we always need deterministic execution. We always want to agree on the state, so we cannot choose our randomness ourselves. What we do is that a subnet creates random tape artifacts every round, which are threshold BLS signatures. The random tape artifacts are created, they go along with the finalized height, which is very important, such that the randomness is created only when messages are set in stone. They no longer be taken back. And from this random tape, canisters can request secure randomness using some API that we saw, and they will get an answer in the next execution round, which will be then secure, independent randomness that they can use. That's it for me. Thank you for your attention, and maybe we can go to some questions.
Great. Thank you so much for that, Manu. We do have a bunch of questions that I want to get through. So the first question, I actually am not super familiar with this. So Manu, hopefully you're able to understand this question better than me. So what do you think of Cloudflare's approach of having a wall of lava lamps and taking occasional photos of the wall to create the seed for randomness? So I didn't know that this is possible.
Okay. Okay, cool. Yeah, that's a good question. So there are many ways you can find randomness, right? You can look at also, I mean, people propose looking at the stars and looking at all sorts of things to find randomness. So this definitely works. The challenge is that if you run your smart contract, your dApp on the internet computer, I mean, how you need to query. Suppose we want to use this service that we trust Cloudflare, right? And Cloudflare, let's say they offer this randomness. We now need to agree which sort of moment of randomness we use from Cloudflare, right? It needs to be unpredictable. So this property that if I place my bet, it needs to be, at that point, I must not know yet. I must not yet know which random value will be used to process my bet. So what you could do is something like, okay, if I place it now and I know that it's now, it's now 8 p.m. So at 9 p.m. we're going to use the time at 9 p.m. of Cloudflare's randomness beacon to process this. This could work, but you need to have some margin there, right? Because if you would say I use it at exactly 8 p.m., but maybe there's a slight drift in clocks, and now I can already cheat again. So you can do something like that, but there's a bit of trade-off between. It'll be a bit slower, right? Because you cannot use it at the next second. And if we build it into the system like this, then the delay is literally 1 second. So yeah, because the random tape goes in lockstep with the finalized blockchain, you can wait exactly as long as you need. I hope that answers your question.
Cool. Thank you, Manu. And we also got a comment in the chat during your presentation. It said, "This is making my brain melt. Makes you appreciate more the systems that keep us secure." Amazing. Great. So Manu, next question. What is the best way to use synchronous randomness?
The best way to use synchronous randomness. So I guess what you mean is if you were to write a canister smart contract, that you could immediately request randomness and get something back, right? Well, so I guess, for example, what you could do is, I mean, that would mean that I can go to such a cycles.bet type style website, and I could play, and I don't need to wait for some event to happen. I could immediately know whether I win or lose, right? So you can build very low latency things. And of course, the bet thing is kind of boring, but you can think of all sorts of cool. I mean, for example, all these NFTs I think are generated, right? So you could things where you say I want a random one, and then on the spot it generates one for me, and I immediately know whether I got a rare one or a common one. I don't know. I think you can imagine things like that, or I don't know. In video games, you can maybe get random rewards for things. There's a lot of opportunities where you like having quick access to secure randomness. I could imagine there's a lot of use cases for that.
Great, thank you, Manu. So next question, in the step where the random tape is used to generate PRNGs on the replicas, how do the replicas all agree on the generated random number?
Okay, yeah, so that's a good question. So let me, you're talking about this slide basically, right? You can do something very simple. For example, I have to admit, I don't know by heart exactly how we do the derivation, but one simple solution would be to take this random tape as a seed, and now I create new seeds, like derived different seeds from that. For example, like I hash the random tape with the number 1, and that gives me the seed for the pseudo-random number generator 1. And I hash the random tape with the number 2, and this gives me the seed for PRNG 2, and so forth. And now I can use these random number generators that are seeded. So everybody can do this in the same way, right? So everybody will come up with the same seeds. And now, because we are in the deterministic processing part of the system here, right? So we are processing messages that made it through consensus. So everybody agrees on which messages to process, and those messages will trigger the same randomness requests in each thread. So every replica will give the same random or pseudo-random answers back.
Okay, thank you. Thank you, Manu. So next question, can you explain again why using the random beacon for randomness is insecure in the context of canisters getting access to secure randomness?
Yeah, so I put that. Yeah, okay, good. So the issue is that the random beacon must grow with the tip of the blockchain. That is because we use the random beacon as sort of a key ingredient for us to make our blockchain. The random beacon says which replica is supposed to make a block. So the random beacon must always grow together with the tip of the blockchain. But the problem is that the tip of the blockchain is not yet agreed upon, or it may not be agreed upon yet. So in this picture here, you see that there's a small fork at the end. There are still two paths that the blockchain can grow. And this means that there are messages in those blocks that are not yet final. They may or may not end up in the real blockchain. At the same time, I can already exactly compute what the resulting state will be of each branch of the blockchain. And that is because I can see the block, I can see the random beacon, I can see the previous state, and this is everything I need to compute to see exactly how things will develop. So if in the top branch, in the top fork of the two forks of the blockchain, I place my bet, and in the bottom branch, there's no bet for me, then already at this point in time, I know whether my bet is going to succeed or not. Because as I said, I can do the whole execution in my head and see whether how it'll play out. And the fact that I know that whether my bet is going to work or not, before it's part of the finalized blockchain, that is a big issue, because now we can still influence whether it will become part of the final blockchain or not. So essentially, I already know if I'm going to win or not, and now I can choose to place my bet. Clearly, this is not going to be secure. And the main difference with the random tape approach that we see here, so this is a very similar picture as before, but you see that random tape thing at the top is not yet generated. And that is because we generate the random tape only when we observe finality. So only when we know that the blockchain is set in stone, it can no longer be changed, only then is it generated. And so that means that at this point in time, when there's still forks, nobody can know how the bets in each of the fork would play out. So you can try to bias whatever you want, but you cannot, you will not know which branch your bets would do better than the other.
Cool, thank you, Manu. So next question, how is this model of randomness that you described in your presentation different than, for example, if I were a developer who built, let's say, a lottery application on Ethereum or another such blockchain platform? Is the method of randomness different between the Internet Computer and other blockchain platforms?
Yeah, so I don't think that, so for example, Ethereum, I don't think offers such a service, right? So not like directly built in. So there are smart contracts that try to do something like this, right? So that's definitely an option. Of course, this is like more difficult, and you need to trust that smart contract does a good distributed randomness protocol, and that you trust the participants that add randomness to that. So I think the difference here is that essentially you get an API to just directly give you secure randomness built into the system. Yeah, which means it's quick, and you don't need to trust any other things or any other parts, and that yeah, basically you don't add security assumptions, and life should be easier for the developers.
Cool. Thank you, Manu. So the next question is super interesting. So how can we prove that the randomness canisters can get access to is true randomness?
How you can prove that? Well, so I guess you can, I'm not sure exactly what part of the system you mean? So speaking as a cryptographer, you can prove that this construction is secure. So you can mathematically prove under computational assumptions that this works. So essentially, the proof is somewhat like, we know that a BLS signature is secure. You cannot forge this signature. There's a proof for this. And even in this threshold BLS setting, you can prove that nobody can find the random tape. Nobody can find the random tape before the time is right. So before the finalized chain has grown far enough. So this you can prove by this is the security proof of the BLS signature scheme, and because that signature is unforgeable, you can predict it. That means that the hash of it is a good random value that is not predictable. Yeah, so I guess if you just inspect the system and look at the source code and the designs and the academic proofs, then I think that combined should hopefully convince you that the randomness you get is secure.
Okay, thank you, Manu. And Paul Liu from the Dfinity team also chimed in the chat saying Chainlink offers randomness through VRF. It is a much simpler model because it relies on an off-chain operator, Oracle, that has some secret that no on-chain component knows about. Whether that model holds water when there are active attacks remains to be seen. Cool. So next question, Manu. Is there any way malicious actors can intercept the process around randomness to be able to provide a skewed result?
Yeah, that's a very important question, right? So this is exactly what we want to avoid. And here, this cool property of BLS signatures comes in, which says that they are unique. So unlike many other signature schemes where there is some randomness involved, like I have many different choices how I'm going to sign a message, in the BLS signature scheme, there is no choice at all. So given a public key in the message, the signature is fully determined. There cannot be multiple valid signatures. And so this really removes all the possibility of bias, right? Because the only choice that you have if you're contributing to the random beacon is, or the random tape, is whether you participate or not. But you cannot give like you have no choices in how you participate that can influence the final result. Because as I said, there is only one valid signature. Yeah, so essentially you can see it as it's already determined, but not found yet.
Okay, thank you, Manu. So next question. What are some of the potential weaknesses around this design of randomness, if any? And why didn't we go with a different design?
Okay, so yeah, that's a good question. So I think, well, so I mean, obviously we went for the design because we think it's a good design, right? The one potential downside that you could argue is that we always do this effort every round of creating a random tape artifact, independent of whether messages need randomness. So maybe a subnet has a lot of canister smart contracts and none of them ever needs randomness, and still the replicas every round do this work of creating the signature. I think that you could argue is a downside. At the same time, I don't think it's a big downside, right? Because it's very, it's not that much work to create this. And for other purposes, we already do this. We already have this special key material set up. So it's kind of relatively cheap in the system to do this. And the advantage is that, so the downside is that we do it even if there's no messages. But the upside is that if there's a million canisters that want randomness all the time, the work for the replicas of the subnet doesn't really increase, right? We already have a good random seed all the time, and now we can derive as much pseudo randomness from that as we want. So I guess the work is kind of constant. It's a downside if you have not so many randomness requests, and it's an upside if you have many randomness requests.
Cool, thank you, Manu. So the next question is asking, Manu, are there any sort of use cases that would involve randomness on the IC that you would like to see developers build that haven't been built yet?
Yeah, so that's a good question. And so I'm not sure if I'm creative enough for this. So I guess the one thing that I thought about was this NFT use case, right? Like I think the exciting thing is I think now often they're like pre-minted and you they're just distributed. And I think it would be really cool if you could have a system where you're like you can buy in, and then it's really like on the spot generating something for you what you get, right? And you don't know yet what's going to be generated, and you don't know how many of something there will be, but you maybe know how unlikely it is that you reach the one that you got, something like that. I think that would be like a very simple and simple but cool application in the short term. Yeah, and I guess in the long term, there's going to be much bigger applications that I cannot come up with on the spot.
Cool. Yeah, no, it's an interesting thing to ponder for sure. So we got a question in the chat where someone was asking when and where will this be available for canisters? Is it available today?
That's a good question. It's available today. You can build on it right now. So these, I'll go back to this page. So you have some links here. Maybe somebody can put these in the chat. But so these SDK pages tell you how you can use this. There's a nice Motoko library that makes it very easy for you. Yeah, so you can use this right now.
Okay, let me see if I'm quick enough to be able to pull up this in the chat. Oh, thank you, Maddie. So fast. Okay, so we have 2 remaining questions unless some additional last minute questions come through. The 2 remaining questions are not specifically related to randomness, but they are related to cryptography, so still within your wheelhouse. So first question, hi Manu, thanks for the presentation. I am not a cryptographer, but are there other projects, blockchain platforms that you think utilize especially interesting or strong cryptography? Do you think the internet computer's cryptography is stronger, or how does it stack up compared to other potential competitors?
That's a big question, and I think I need to watch my words here a little bit. I don't know. I don't want to maybe go too much into direct comparisons with the competition, and definitely not say bad things about any other projects, right? Because there's a lot of cool things out there. I think what sets the internet computer and Dfinity apart is that we have really a large amount of world-class cryptographers working on this all the time. Like this is the only thing they work on. So I think all of our cryptography has been very thoroughly, very, very closely analyzed and proven. And I guess you'll see more and more papers, more academic papers appearing. And we already have one, for example, for our consensus paper and the distributed key generation, where you can see that people went really into great detail, formally analyzing security and proving that everything satisfies the security goals that we want. And I think that level of thoroughness is, of course, something that I guess gives me a lot of confidence that that things are done correctly.
Cool. Thank you, Manu. And our final question, unless anyone has any last minute burning questions. So this is around a previous talk that you've done on consensus. So Manu, I watched one of your talks around consensus. What is the name for the internet computer's consensus mechanism? Is it like there's like proof of work with Bitcoin and proof of stake with Ethereum? And also, can you talk about how the consensus mechanism with the internet computer differs from other blockchains, if there are any sort of pros or cons?
Okay. It's another big question. So as for the name, I think we just call it in the latest paper Internet Computer Consensus, which is maybe a bit of a boring name, but that I guess that's what we named it. It's a little bit different than traditional proof of stake, right? Because it's not that anybody that has stake can directly participate in the consensus mechanism. Instead, we elect nodes through our governance system. So the governance system is where your, stake, your locked up tokens gives you voting power. And then via that, you select the nodes that will represent you in the consensus mechanism, essentially. And I think there was a question about how this maybe compares to other consensus protocols. I think one thing that's interesting is that our consensus mechanism is actually relatively simple. It's relatively straightforward. So that makes, so security analysis is always hard, right? But it makes it rather, I guess, slightly less hard to argue the security of this. And I think what's nice is this use of the random beacon and the ranking of the block makers, such that if certain block makers or certain nodes are malicious or don't participate, kind of the fallback is immediately built into the protocol. So in all other protocols, like they work well and they're kind of easy to follow as long as everybody does their job. But as soon as some nodes start misbehaving, things become very difficult to analyze, or maybe they become even like computationally expensive or slow. And in the internet computer consensus protocol, this is kind of built in, right? We don't elect one block maker. We just have a ranking, right? And so if the first one doesn't do their job, then the second one comes in, and so forth. So I think that's one part that I like. And I think by far the most important one is the fact that it's actually safe without making networking assumptions, right? So a lot of blockchains depend on seeing the longest chain, right? Or seeing the chain with most work. And this, of course, always relies on you actually being connected and seeing all the candidates, right? Because only when you have all the candidates, you can find out which one is the best one. And I think that is very limiting, right? Because then if your internet connection doesn't work for a bit, suddenly you might be tricked into believing the wrong chain, right? And because of our finalization signatures, this can never happen in internet computer consensus. You will always know just by seeing the cryptographic material what the real chain is. And I mean, maybe you're behind because your internet doesn't work, but you will not believe a false statement because of that. And this also makes it much easier for external clients to securely interact with the blockchain, because we work with signatures, not with finding the longest chain. So it's also very easy for lightweight devices to get trustworthy information out of the system. Whereas in some other blockchains, you would need to, essentially the only way to get secure information out of the blockchain is by having the whole blockchain, right? But this is difficult on your smartwatch, for example.
Okay, awesome. Thank you, Manu. So we have come to the end of our questions. So big shout out to Manu for such an enlightening presentation. Thank you to the community for such great questions and for tuning in. And we will see you all next time at a future community conversation. Bye, everyone.